Good afternoon. I want to talk about Kirchoffs laws. Sometimes these create difficulties for students. So there are two laws. Let's look at the first one. The first one states that the algebraic sum of the currents at a junction is zero and follows from the fact that electric charge does not accumulate at any point. In other words, it's conservation of charge. So in this slide you can see that the current I1 and I1 is going in, and I2 and I3 are the resultant currents going out. So if you want to do it algebraically, you can say I1 minus I2 minus I3 is zero. So here's an example in the next slide of Kirchoffs' first law. We have two resistors of 3 ohms and 6 ohms connected in parallel across a 6-volt battery. So the first question is, how is I1 and I2 related? Second question is, what is the PD across each resistor? And the third question is, find the values of I1, I2 and I. So the first question, the answer to the first question is I plus I1 plus I2, as you can see from the diagram. Since it's a parallel arrangement, the PD across each resistor is 6 volts. And in the third part, Ohm's law gives R equals V over I, so we just use one of those branches. So I is V over R, giving I1 is 6 over 3, which is 2 amps. And similarly, I2 is 6 divided by 6, which is 1 amp. So the total current I is 2 plus 1 equals 3 amps. In the next slide, we get Kirchoffs' second law, which states that around any closed loop, the sum of the EMFs is equal to the sum of the PDs. Mathematically, we can write circuit EMF sigma of E is sigma of IR. And here's a simple example, just to show the question in symbols rather than numbers. So if we look around the loop, we've got two batteries, E1 and E2, and they're both pointing in the same direction. They're both giving current in the same sense, or voltage. So we add them together, E1 plus E2. And then going around the loop now, we have I1 going through the internal resistance of R1, so that voltage would be I1 R1. On the left-hand side, going down, we've got I2 current going through resistor R1, so the PD across there will be I2 R1. Going across the bottom, we've got current I3 going through resistor R2, beg your pardon, which is then I3 R2. And going up on the right-hand side, we have current I4 going through resistance R2, so that PD there is I4 R2. So if we follow that in the red, you will see the equation that we need. The second example is more numerical. We've got three resistors, 3 ohms, 4 ohms and 5 ohms, all in series. And we've got two batteries, one of 2 volts at the top and one of 1 volt in the middle. And first thing to do is to choose directions of the current in each part and mark them, label the currents. It doesn't matter if you get this the wrong way round, because in the final solution you get a negative answer for the current if it's going in the wrong direction. So applying Kirchoffs' first law to a convenient point, in this case A, go back again, A, yes, that's the on the left hand side there. We get I3 is I1 plus I2, and the upper loop gives 2 minus, so that is 2 minus 1 is 3I1 minus 4I2, second equation, and the bottom loop gives I is 5I3 plus 4I2, as we discussed in the previous slide. So, keeping these on the right hand side in red, we see the three equations we got there. We have we can get two unknowns, so we need three equations simultaneously to solve them. So from 2, 3I1 minus 4I2 is equal to 1. So I1 is 1 minus 4I2 divided by 3, and I3 is 1 minus 4I2 over 5. So substituting in these equations in 1 gives the result shown, and multiply by 15 to get rid of the fractions 5 and 3, we get the middle equation, and we get 47I2 is minus I2, giving I2 as minus 42.5 milliamps. The minus sign shows that the current I2 flows in the direction opposite to that initially shown. Hopefully you'll find this useful with your physics, and thank you very much for listening.